back, and it's been quite some time since I've uploaded a video. I've been working on many projects since my last. I suppose I have uploaded 2 shorts, so I think at least you have an idea of what I've been working on. And then obviously there's a lot of other things as well going on. But we've got computer architecture coming up next semester, and so I was like, okay, I should probably do a little bit of review, right? And so I was kind of going over Mux and Dmux, and I realized something. Normally, when I'm learning, I like to take a first principles understanding to everything. If you've been watching this channel, you probably know that. And so I realized something. I'm like, wait a second, I can't actually implement the composed versions of the multiplexer and the demultiplexer, right? I understand how to come up with the mux and the demux from first principles, right? The basic primitive versions. But to put them together, right, into larger muxes and demuxes, I was struggling to do it, right? And then I stumbled across the Holy Grail, right? So I'll be sharing that with you guys today. So I guess I'll put this video as the Introduction to Digital Logic 3. Yeah, seems appropriate. So let's just start with this because I don't have a lot of time, unfortunately. So we'll start with what is a multiplexer, right? And so it's just a chip. It's going to take in more than one input. In our particular case, 2 if it's a 2-to-1 mux, right? Because if you have a single bit, you can only represent 2 states with that bit, right? 0 or 1. So you can select one of 2 inputs, right? 2 to the n. Okay, and should all be like fairly standard to you by now if you're taking digital logic for any time. But if you don't know that, then okay, now you do. And the demultiplexer is simply the inverse operation of that. It's going to take in a single input and it's sort of routing it, right, to somewhere else. And again, you have a select line, and the select line is going to select, right? If you've got a single select line in this particular case, well, you can only represent the 2 possible states with a single bit, right? So you can either send it to y0 or y1 here. And the truth table for our multiplexer looks like this, and so it should be fairly straightforward to you by now. We've got 3 inputs, a single output, right? The select bit when it's 0, and when the input is 0, then obviously we're going to pass this value through, right? So fairly stock standard, I feel like. The x here just means that we don't care about this value, right? Because since we know that we're passing in this anyways, whatever I1 is in this particular case for this input is completely irrelevant. And so the same logic will carry through for the others. And we've already gone over, once you have the truth table, it's very standard how to get the Boolean expression, right? So not s and I, or s and I1. So, and then you can come back and reference this, right? So I'm not going to spend too much time on that. I feel like it shouldn't be too difficult to derive the Boolean expression for the mux. But demux, if you don't have any experience yet. Oh, right. So let's look at the gate implementation. Okay, my PowerPoint thingy is, yeah, Linux is not behaving itself today. But okay. The gate implementation for the multiplexer is obviously just an extension from the Boolean expression. So, and I've already harped on this so many times before, and retrogate analysis, right? Look at the most important gate or the last gate. So in this particular case, it's OR, so we know our OR gate. And then you work backwards, and okay, we see we've got 2 AND gates. So obviously we need 2 AND gates to feed into that OR gate, and then the inputs are exactly as you would expect them from the Boolean expression. And so we can talk about the demux now, hopefully. Is this? Yeah, for the demultiplexer. So if you've never seen this before, it might be a little bit daunting because the only thing different about the demultiplexer is that you've actually got multiple inputs now. So it might be a little bit novel, but it's the same standard procedure, right? So you've got 2 inputs in this particular case, right? D, you can say, is your input line, and S would be your select line. Now what the demultiplexer is going to do is route the data, right? And so if the select line is 0, then y0 is going to be 0. It's going to collect this one, okay? And this is going to be 0 as well. And if the data line is 0 and the select line is 1, same case here. The important thing though, what happens with the demultiplexer is if your data path is on, right? We don't really care what happens when the data is off, to be honest with you. But When the data is on is the important case and the select line is 0, right, we need the data to route to y0, okay, and then to y1 is going to be 0 like this. So you're sort of manipulating two outputs at the same time, and that might be a little bit novel if you haven't seen this before. It might seem strange, but it's not too complicated, hopefully. And if we got 1 and 1 here, right, well, this just means select for the second input, right, so pass the data to y1 instead. So hopefully that's pretty straightforward. And the Boolean expression now is where it might be a little bit tricky if you don't understand, but it's just two separate inputs, right? So we've got just put the sum of products together. Well, there's no sum in this particular case, right? Just the two products for each input. So you've got two separate inputs, y0 and y1, like so, and the gate will look exactly like this. And you can see we've got the two separate inputs here, and the diagram is certainly not to the best, but yeah, it's legible. And I don't know what happened there. Okay, now let's talk about composing the muxes. Oh, I need to look at the time. Okay, I've got like 5 minutes, 10 minutes. Yeah, I don't have much time, which was what sucks about this, but just trying to rush it. So how do we get a 4-to-1 mux, right? We know how to get a 2-to-1 mux, but how do we get a 4-to-1 mux? And what you do not want to do, right? You could do this if you wanted to, which is actually what I did on the first time I was building my CPU, right? I needed a 4-to-1 mux, and I was like, okay, here's what I'm going to do. I'm going to do the same procedure I did for the 2-to-1 mux, right? I'm going to increase the number of inputs, right? And the truth table is going to become horrendously large. Do not do that. Yeah, so that was a lesson I learned the hard way. Unfortunately for me, well, I guess fortunately I do know it now, but like fortunately for you and unfortunately for me, but you can compose these muxes in the following manner. You just take the 2-to-1 mux, right, and you feed it into a third mux like this, exactly as this diagram. So you have a 2-to-1 here, a 2-to-1 here, so you have a total of 4 inputs, right, and you have 2 select lines now. The first select line will be responsible for which value you're going to send across each of these muxes, right? So say for instance we wanted to select in truth I1, right, then we would select that for both of them. So we would send I0, sorry, not I1, I meant to say I0. We would send I0 through this mux and I2 through this mux here, right? So that value is being passed onto the bus here, and I2 is being passed onto the bus here. And then we need another bit now to select out of those two. And then again, it would be 0, 0. So 0, 0 would give you I0 being passed out. I'll put here 1. And then you can go through all of the other cases as well. And then obviously now you should know for 4 inputs, right, a single bit is no longer sufficient. We needed another bit, right? So hopefully that's clear. So 2 to the n again. Okay, and so composing the demultiplexers is the same thing again, right? And you should know, since they're inverses to each other, you can compose them in the following way. All right, that's fairly straightforward. The thing that occurred to me, right, is that I would always have to memorize this configuration, right? This particular configuration and this particular configuration. I'd always have to memorize it, and to be fair, I don't have the best memory, and I have many different things that interest me. So at any one particular given time, I could very easily forget something like trivial, and then I have to go look it up again, right? And so what I actually ended up noticing, right, because I was drawing it, and I realized that, wait a minute, this is a binary tree, right? And so I was like, okay, this is like, I no longer have to memorize it, because I only have to know what the demultiplexer structure is, right? And so you don't even have to learn the multiplexer. Learn the demultiplexer structure, and it's a binary tree like this. This is a demultiplexer. Every single node inside of your binary tree is a demultiplexer. Okay, and so in our previous example, right, where we wanted to route data, right, to 4 paths like this, you saw that we needed 1 demultiplexer and it needed to go in like this. Let me see if I can go back and find that for you. Right, like this, right? So this is what it looks like. And then this can just keep going on like this over and over again. And it's like so nice, like once you see what's going on. And then you can start abstracting these into boxes as well. And that's the key idea. If you can see a demultiplexer as a binary tree, you're good to go. And then obviously the multiplexer is just the reverse operation of the demultiplexer. So instead of going down the root node, right? Instead of traversing down the root node, you're traversing up, right? From the leaf back up to the root, because it's the inverse operation. And this time the leaves will serve as your input, right? And it's going to feed up through the tree all the way to the node to pass to, well, your node will be your single output in that particular case. And yeah, that's it. It's got a lot of applications in cryptography, right? Actually, there's a lot of linear algebra. I didn't get a chance to look into it because unfortunately right now I'm heavily focused on robotics and control systems. And so I don't want to like scatter myself too much or spread myself too thin. So I will come back to this because cryptography is something that interests me a lot. And to learn that there's this like elegant of a way to connect linear algebra to cryptography is something I just was not aware of, and so I will come back to this. And yeah, so there are a couple of key takeaways here, and yeah, I think you can read those for yourself, right? I'm not here to read slides to you. I just wanted to explain or to hopefully make you aware that you do not have to memorize these composed structures for a 2-to-1, you know, and all the way up for your muxes and demuxes. Just look at your binary tree. Imagine a binary tree, right? And that would be your demultiplexer. And you're selecting, right? You're routing down for the demultiplexer, and then you're routing up for the multiplexer. And it's so nice. It's so elegant. Okay, well, thanks for watching, and hopefully that made sense. If it didn't, I'm sorry. And I probably apologize for some terrible audio quality as well. I have no idea. Okay, and that's it from me. I think I'm well and truly out of time at this point.